Hey, good morning, physics students. We are going to go through forces and the introduction to Newton's laws of motion. So forces and Newton's laws, the things we're going to cover today are going to be forces, Newton's 3 laws of motion and what they mean, and then we're going to touch on just very briefly force gravity and types of contact forces. The thing we're going to talk about is net force. And what net force is basically the sum of all the forces acting on a body. So force net is the combination of each force acting on an object. And what we do is we add those together based on which direction they're coming from. So for instance, if you're sitting in your chair, there's a force gravity pushing you down. That would be one force. There is a force from your chair, which we're going to call the normal force, and we'll talk about that here in a minute, that would be pushing you up. Those are acting in opposite directions, so those forces would cancel each other out. So our net force would be 0. Okay, free body diagrams is going to help us see what forces are on an object at any given point in time. So the way we're going to do those is we're going to basically follow 4 steps to draw our free body diagram. And we're going to walk through that, but I want to give that to you instead of in words. I want to give that to you in a drawing. So we're going to walk over to the next little slide. Okay, so this is going to be our first drawing of a free body diagram that I want you to see. So forces we have acting on an object. Picture this object just sitting on a table and there's a string attached to it pulling it to the left. So object sitting on the table, it's getting pulled to the left. There's going to be 4 forces acting on it. You have force gravity acting down. You could also think of that as weight. So force gravity acting down. Going upwards from the table is what's called force normal. And this is a force just from the surface that's essentially preventing the object from falling through the surface. Going left, because we're pulling on it, and probably pulling on it by a string, that is going to be the force tension. So anytime you have a string or a rope, you're going to have a force tension. And to the right is going to be what's called force friction. And so if you have friction, that is going to be acting usually in the opposite direction of the motion of the object. All right, Newton's first law of motion. So Newton's first law of motion is really simple. There's a couple things to it. We're going to walk through those. So Newton's first law, if there's no forces acting on an object, the speed and the direction of its motion doesn't change. So if an object's just moving and there's no forces acting on it, it's going to continue to move in a straight line at that same speed forever. There's a second term we're going to talk about is inertia, and it's the measure of an object's resistance to its change in motion. So here's what that really means. If you have a large mass, it's harder to get you to move. If you have a small mass, it's easier to get you to move. If you have a large mass, it's harder to stop you from moving. If you have a small mass, it's easier to stop your motion. A way to think about that, it's easier for you to start moving a car than it is a bus if you're pushing on it. The reason is it has a smaller inertia, which means it has a smaller mass. Okay, so Newton's first law of motion, we're just going to kind of walk through this, what it means. So if an object's at rest, which means it's not moving, it's going to remain at rest. If an object's in motion, it's going to continue to move in motion, and it's going to move with a straight line with the same exact velocity. So the only way that changes is if a force acts on it. So no force is required to keep it moving in a straight line, as long as friction is negligible, which means friction is 0. We're going to talk about this term. An object is in translational equilibrium. So equilibrium means everything is balanced out. And that happens if the net force on an object, which means all the forces added together, equals 0. And then just a reminder down here at the bottom, the bigger an object's mass is, the bigger that object's inertia is. And then I just put down net force equals 0. We have what's called translational equilibrium, which means all the forces cancel out, and it's going to do one of 2 things, either stay at rest or stay at the exact velocity it's traveling at already. Okay, Newton's second law of motion is really straightforward, and it's really just this equation. So the net force on the object is equal to its mass times its acceleration. So here's what it means. If you have two objects and one has a large mass and one has, so here's my first object, we'll say it's got a small mass. We'll say it's got a mass of 1 kilogram. We've got a second object that has a bigger mass. It has a mass of, let's say, 100 kilograms. So it's got a mass of 100 kilograms. The one that's going to accelerate more, say we push both of these with a force. We say the force equals 1 Newton. So 1 Newton of force for this box, 1 Newton of force for this box. Which one will accelerate more? Which one's going to have a bigger acceleration? Well, if we look at it, the force is exactly the same, but the mass of the second one is much bigger. So the acceleration for the second one will be significantly smaller than the acceleration for the first one. Okay, just kind of a follow up on Newton's second law. So object's mass, remember mass and inertia are interchangeable words. So you may see mass or you may see inertia. They referring to the object's mass. If you have a bigger mass, you're going to have more force to get to a specific acceleration than if you had a small mass. So that should make sense. It's really going to be more difficult to push something that has a large mass than it is something that has a small mass. Down here, we're going to talk about what's this term again, equilibrium. This means all of your forces are balanced out, and we can really have two types of equilibrium. One happens when the velocity is at 0, and it's called static because you're just in one place. You're not moving. You can also have what's called dynamic equilibrium. This happens when your velocity is not equal to 0, but it's constant. A good way to think about that is think about your car on cruise control. Your car on cruise control has a velocity, whatever you set it at, and that velocity is not changing. So it's constant. So since it's in motion, it's called dynamic equilibrium because its velocity is staying constant, which means the force is pushing it forward. So your engine versus the force of friction are canceling each other out, so it maintains a constant velocity. All right, the third law of motion is really, really simple. For every force, there's an equal and opposite force. So here's a way to think about it. If you sit down in a chair and the chair doesn't collapse, you have a force of gravity pushing down on the chair. The chair has a force pushing back on you. Those forces are equal to each other. So a way to think through that, a force on a second object, on object 1, is equal to the same force that object 1 puts on object 2. Now here's a common way they like to ask this, and I'll give you a minute to think about it. Say here's a giant bus. Here's my bus. Here's my bus. It's driving to the right. And here's a bug, really small bug. And the bug hits the windshield. So take a second. Which one experiences a bigger force, the bus or the bug? Well, if you look at Newton's third law on this, there's going to be an equal but opposite force. The bus and the bug both experience the same amount of force. Because for every force, there's going to be an equal and opposite force. And I just want to walk you through some of the common type of forces we're going to see this year. Contact forces. We're going to talk about normal force and friction. We're going to talk about tension, and then for gravitational force or force gravity. So contact forces first. Contact forces happen when there's an interaction between surfaces of an object. So the objects have to be physically touching each other. That's the way we get a contact force. There's a couple of them we're going to talk about that we're going to see quite a bit this year. The first one is what's called normal force. This happens when basically an object is touching a surface. So normal force, this is just picture a box sitting on the ground. The normal force is always perpendicular or at 90 degrees to the surface. So normal force here is pointed straight up. Now you notice when we put it on a ramp, the normal force is off at an angle. However, it is still 90 degrees to the surface that it's sitting on. So normal force is one type of contact force. Take a look at this again. Normal forces, now we just have a box sitting on a table. We have a normal force going upwards, so that's our normal force. And then we have the force of gravity or force weight pushing down on it. So here's what that means. Since this object isn't moving up and it isn't moving down, the normal force and the force weight cancel each other out to get us to 0. So that is our net force. So our net force is 0, which means force normal and force weight have to be equal to each other because they're happening in a pair, and for every force we have an equal and opposite force in this situation. The second type of contact force is frictional forces, and we're just going to kind of walk through this. We're not going to go through all of the equations about it, but I have them here. So you have two types of friction, what's called static friction, and this prevents an object from moving. So think about like if you go to try to push something and it doesn't move right away, you still haven't overcome static friction. So picture like you're trying to push your car because it's not running. At first, it's really difficult to move. You're trying to overcome static friction. The second type of friction is called what's called kinetic friction. So this is the friction required to keep an object moving that is already in motion. So think about you've just gotten your car moving and now it's actually rolling. It's usually easier to keep it moving. So static friction is going to be more than kinetic friction. And I've got that drawing for you here on the next slide. So frictional force, you'll notice, force applied. So static friction goes up, and at some point you finally overcome static friction and the object starts to move. Then the dynamic friction is going to stay constant the entire time it's moving. So static friction increases until you get it moving, and then dynamic friction takes over, and it's going to be constant, but it's going to be less than your static friction. All right, the last force we're going to talk about is called force tension. And here's the main thing I want you to know about force tension. It always comes through a rope. So if you see a rope or a string pulling on an object, lifting an object, think force tension. And one of the things with these problems, we are always going to assume it's an ideal string or an ideal rope or cord, which means it doesn't stretch, and which means the cord itself doesn't have any mass. So that's where we're going to stop for today. And then go ahead and make sure you complete your exit ticket and that you've got everything turned in that you need to have turned in on Canvas. Y'all have a great day. Thank you very much. Bye-bye.